Alrighty, last but not least is the steady state matrix or steady state matrices. Let's just get a few formulas out of the way and then we'll sort of start to explain what's actually going on. So this formula says that the particular state matrix that we're looking for, usually the steady state matrix, is the transition matrix times the previous steady state matrix. We're going to see a lot of this kind of thing when we come into our difference equations module, so it's kind of good to get used to it now. This says the state matrix of n is t times the state matrix of n minus 1, as in the one before the n. Like, say n here was 6, the sixth state matrix, and then this would be 6 minus 1, so 5, the fifth state matrix. So for example, the sixth state matrix is t times the fifth state matrix. The 10th state matrix is t times the 9th state matrix, so 10 minus 1 is 9. So this just means the previous one. We're going to see that heaps when we get to difference equations, so it's kind of good to have that idea now. This n minus 1 thing, or at the bottom, is like the previous one to the n. So n minus 2 is obviously 2 before the n, or n minus 3 is 3 before the n. But usually we'll see the n minus 1. If that said n plus 1, which it doesn't, but if it did, that would mean the one after n, like n plus 1 more. So the 10th, and that would make that the 11th if that was Sn plus 1. Nonetheless, I've written here the steady state matrix, but really it's just whatever state matrix we're looking for. Generally it's the steady state matrix. So S of n is steady state matrix, T is the transition matrix, and we saw them in the previous video. If you've got no idea what I'm talking about, you might need to watch that video first. And then the S of n minus 1 is the previous matrix to this one here, the steady state matrix. A different way to write that formula, and this could be more useful sometimes, other times not, is that this state matrix here, the steady state matrix, is t to the power of n, so the fifth one, t to the power of 5 for instance, times s of 0. S of 0 just means the initial, I've written that down here, or the original state matrix. And often in maths we see this 0 thing, meaning the initial, the first thing, the original. And we're going to see that in difference equations too. So we'll see that in t of 0, that'll be the initial term, or sometimes it's t of 1. Either way, when we see this 0, that means the initial term, or the original term, same word. So the theory is, and we've looked at transition matrices already, as a transition matrix is multiplied time and time again, or we apply that transition time and time again, the amount of objects at each location is going to settle and become steady. So, for example, in our previous transition matrix, you might remember we looked at this matrix just here. The theory is, over a long period of time, the different amounts of objects at each place will kind of settle so that it doesn't matter what's transitioning where, they'll stay constant. Instead of starting with 100 here and the next time there's only 50 there because 85% of them went to B and it only got 45% of B's and it only got 10% of the C ones, so it might have a few less than 100. In the long term it'll work out so that each spot on that A, B and C will have its own amount and it won't really get affected by these transitions anymore. It'll settle, it'll become a steady state. So that's that steady state theory we're working on. So another way to say that is eventually the amount or percentage at each part of the matrix will stop changing, and that usually happens after that transition happens about 15 times, usually to be safe in our calculator, because we can put any number in our calculator, we'll do it quite quickly. I like to say 150 instead of 15, and that'll really sort of lock down and make sure it's 100% steady, but it's usually accurate to like a couple of decimal places, which is enough, after about 15 transitions. So it's important to note, I've just written that down here, that the initial matrix, this S of 0, doesn't actually affect the steady state. The answer's going to be the same no matter what. So what I'm saying is it doesn't matter if there's 100 objects altogether and 50 start here, 20 here and 30 here, or it doesn't matter if all 100 start at B, or it doesn't matter if 80 start at C, 20 start at B and none start at A. It doesn't matter where the distribution starts, it will end up having the steady amount in the same place no matter where they start. That's a pretty cool function, I reckon, and we'll sort of see that happening over and over again. What that really means is it doesn't matter what this S of 0 looks like, it just matters that the total amount, so if we're talking about 100, we're talking about 100. or if we're talking about 150, there's 150. As long as that amount is the same, it doesn't really matter where in that transition matrix it starts. So often we just count the total in an initial matrix. Let me show you what I mean. Here's our example. And our initial state matrix here is 80 and 20. It wouldn't matter if it was 20 or 80. In the long run, by the time we get to a steady state, it'll even out and make no difference what it started as. But it has to stay with 100 total objects. So here's our first example. Here's our transition matrix. 85% start here and end up here. Start here and 15% start here, and we've got all these different distributions. And again, remember we said they had to add up to 1 or 100%. There they are there. 0.05 plus 0.95, that's 1. 0.85 plus 0.15, that's 1 as well. So it says find this distribution of these things after 1 day, or after this transition has happened once. So we put that into our formula that we saw on the last page. S of n, that's the day we want, is t times the previous day. So after 1 day, we're looking for this S of 1. So the first day after that, the first day has passed. So obviously the day before that is S of 0. So 1 minus 0. So in this case, our n, you can see, is 1. S of n is 1. So 1 day, n is 1. So let's put that into our formula. S of 1 equals t times S of 0. So the day before. So the first day is a transition matrix times the previous day, which happens to be the initial day. So S1 is t times S of 0, and I've just written that down here, t times S of 0. From here, I just put that all in my calculator and it would tell me that was 69 and 31. If you're dying to do that manually by hand, you could, but I wouldn't bother personally. You could check it if you wanted, I guess. So we started off in the initial day with 80 and 20. And after 1 day, S of 1, we had 69 here and 31 here. Let's see what happens after 2 days. We'll see we're sort of getting closer to a steady state. So the distribution after 2 days, that makes that S of 2, this S of n, S of 2 now. And the day before, obviously the day before the second day is the first day, S of 1. So the second day is the transition matrix times the first day, like the day before. So I'll just put that in my calculator as I'm getting used to doing now. S of 2 equals t times S of 1. Put it in my calculator and it says 60.2 and 39.8. So after 2 days, remember we started with 80 and 20. Let me show you that here. We started with 80 and 20. After 1 day we had 69 and 31. And after 2 days we had 60.2 and 39.8. Depending on how observant you are, you might notice that this went down, about 11. And the next day it went down from 69 to 60.2, so it went down about 8.8, like a bit less. Just like the first day this was at 20, and the second day it went up to 31.